I want you to try and put yourself in a very specific, highly uncomfortable situation for a minute.
Oh boy.
Yeah, bear with me. So if you're listening to this right now, maybe you're on a commute or sitting at your desk, but I want you to mentally transport yourself back roughly 20 years.
Okay, setting the scene.
Right. You're a systems administrator. It is 3:00 a.m. on a Sunday. You are standing inside this massive, cavernous corporate data center.
Not a fun place to be at 3 a.m.
Definitely not. The ambient temperature is hovering somewhere around 60 degrees Fahrenheit, but, the wind chill from those massive HVAC systems blasting down the aisles, it makes it feel so much colder.
And the noise. The
Yeah.
noise is something you never really forget.
Oh, absolutely.
It isn't just a hum, it's this deafening physical roar of thousands of industrial fans spinning at maximum RPM.
Yeah, you physically could not have a normal conversation in those aisles without screaming at the top of your lungs.
You'd lose your voice in 5 minutes.
Exactly. So you're freezing, you're deafened by the roar of these servers, and you are exhausted. But here is the part that, looking back from where we sit today, it feels almost like dark comedy.
The crash cart.
The crash cart, yes. To fix this mission-critical server that just went down and woke you up, you are physically pushing this rickety, heavy metal contraption down the narrow aisles.
A literal metal rolling cart. And they always seem to have like one wheel that locked up or squeaked constantly.
Every single time. And on this cart, you had this massive, heavy cathode ray tube monitor, right? Plus a wired keyboard, a mouse, and a KVM switch with this tangled rat king of VGA and serial cables just hanging off the back of it.
It was a complete mess.
So you're pushing this cart down these freezing aisles, squinting at the serial numbers on the racks,
Okay.
just trying to find one specific physical box out of thousands.
Needle in a very loud, cold haystack.
Right, and when you finally find it, you have to stand there shivering, manually plugging the cables from your cart directly into the physical ports on the back of that one single server.
Just to get a command line prompt on your monitor, just to see why the database crashed in the first place.
Exactly. And the source material we're looking at today uses the word draconian to describe this era. And frankly, I feel like that might be an understatement.
Oh, it's absolutely an understatement. I mean, managing enterprise hardware at scale back then required immense physical labor.
Yeah.
It was completely localized, inherently slow, and, well, when you're dealing with a global outage, the time it took to physically reach the hardware could cost a company millions of dollars in downtime.
Just because you had to walk down a hallway.
Yeah.
And the reason we are starting with that visceral image of the shivering admin and the tangled crash cart is because of the sheer magnitude of the contrast with where the industry is heading right now.
It's night and day.
It really is. So we are unpacking a highly detailed presentation today. It's by Kevin Kulp, the PM head of cloud management solutions over at Supermicro.
Right, and he's specifically talking about SuperCloud Composer, or SCC.
Yep, SCC.
Yeah.
But the implications of this technology, they go way beyond just a software pitch.
Definitely. What Culp is really mapping out here is the complete architectural philosophy of modern global enterprise management.
Which is a lot to unpack.
It is. We're essentially looking at the mechanics of how the largest digital infrastructures on Earth are actually kept alive, organized and scaled all without requiring an army of people pushing crash carts.
And for you listening, whether you're an IT director trying to map out, say, a 5-year hardware refresh strategy for your company, or you're just intensely curious about the physical reality behind the cloud, this deep dive is going to clarify a lot.
Because the cloud isn't just magic, it's physical hardware.
Exactly. We're going to explore how the industry transitioned from that localized manual nightmare to what they now call a lights-out enterprise.
Where a single administrator can theoretically provision, monitor, and manage tens of thousands of liquid-cooled AI servers located across the globe, all from a laptop.
Which is wild. And we're also going to look at the fascinating economics that make doing this on-premises viable again.
The lights out concept is really the ultimate goal here. It's a data center where you literally turn off the overhead lights because human beings simply do not need to be in the room anymore.
But achieving that absence of physical presence, that created a vacuum, right?
Yeah, and that vacuum was quickly filled by a completely different kind of chaos.
Because getting rid of the crash cart didn't actually solve the management problem. It just digitized it.
Right.
And that brings us to the first massive hurdle Culp addresses in his presentation. which is this phenomenon of device sprawl.
Device sprawl is basically the modern administrator's equivalent of the tangled cables on the crash cart.
I like that comparison.
Because in the pursuit of scaling up, enterprises just started deploying hardware everywhere. Today, a single DevOps team isn't just looking after a server room down the hall.
Right. They might be responsible for 5,000 compute servers in a facility in Virginia, plus a massive array of storage devices in Frankfurt,
Right.
and then a complex web of high-speed networking switches in Tokyo.
Exactly. And the underlying friction here is that this massive global sprawl is rarely homogeneous.
Meaning it's not all from the same brand.
Right. It's not like a company buys everything from one single catalog on day one and never changes it. They acquire smaller companies, they integrate legacy systems, they hunt for bargains on different types of hardware across an entire decade.
Which means they end up with a profoundly fragmented management environment.
Heavily plagued by disparate tools. To check the health of the compute servers in Virginia, they might have to log into a proprietary web interface built by Dell.
Okay, that's one tool.
Then, to provision a new VLAN on the network switches in Tokyo, they have to open a completely different command line tool built by Cisco.
And to allocate more storage in Frankfurt, they're using a third entirely separate software suite from HP.
Exactly. So the physical crash cart was replaced by a digital workflow that requires an administrator to constantly jump between 10 different proprietary dashboards just to figure out why a single application is running slowly.
The context switching alone must be exhausting, just mentally keeping track of all those different logins and interfaces.
It creates immense latency in the decision-making process. Because when you have disparate management silos, correlating data becomes a manual, human-driven task.
So if the network tool says bandwidth is saturated, but the compute tool says CPU usage is low, the administrator has to manually piece together what is actually happening.
Right. And in a modern enterprise where service-level agreements demand near instantaneous uptime, that delay is completely unacceptable.
Which makes the following statistic from Culp's presentation incredibly counterintuitive at first glance.
Yeah, this one surprised a lot of people.
Right, because we have this massive problem with device sprawl and disparate tools, right? And for the last 10 to 15 years, the loudest narrative in the entire technology sector was that the solution to this was the public cloud.
Move everything to Amazon Web Services, Google Cloud, or Microsoft Azure.
Exactly. Let them worry about the hardware, let them provide the simple dashboard, just rent the compute from them.
Yet, Culp points out that today, 38% of SMB customers, small and medium-sized businesses, are actively choosing to support their infrastructure on premises.
Almost 4 out of 10. They are keeping or moving back to their own physical data centers.
The cloud repatriation trend is honestly one of the most significant shifts happening in enterprise IT right now. The pendulum is aggressively swinging back.
And the source material points to 2 specific, powerful drivers for this reversal. The first one is compliance and governance.
Let's explore the reality of that governance aspect because, well, the cloud is essentially just someone else's computer.
Yep, it's just a data center you don't own.
When you put your highly sensitive customer data or proprietary AI training algorithms onto a public cloud, you're relinquishing a fundamental layer of physical sovereignty over that data.
And depending on the sector you operate in, relinquishing that sovereignty might be literally illegal.
Exactly. If you are a healthcare provider dealing with patient records, a financial institution managing transactional data, or, a defense contractor working with government assets, the regulatory frameworks surrounding data privacy and security are incredibly rigid.
You often have to prove exactly where your data resides physically, like point on a map.
Right. You need to be able to audit the physical security of the facility. You cannot simply trust a multi-tenant public cloud environment where your data is sitting on the same physical hard drives as 100 other anonymous companies.
You literally need to be able to point to a building with your own security guards and say, the data's on rack 4 and we own the lock to the cage.
Precisely. The governance restrictions mandate an air-gapped or at least highly controlled physical environment that public clouds inherently cannot provide without charging astronomical custom fees.
Which brings us to the second, perhaps even more universal driver for this 38% statistic, the staggering rising costs of public cloud offerings.
It really all comes down to the bottom line.
I was thinking about this economic shift, and I want to run an analogy by you to see if it maps to the enterprise reality.
Let's hear it.
Okay, so moving to the public cloud originally felt like moving into a high-end, fully furnished corporate apartment.
Okay.
It is incredibly convenient. You don't have to hire a plumber. You don't have to buy furniture. The utilities are bundled. You just show up with your suitcase, your applications, and you start living.
I like this.
But because it's so convenient, your team starts turning on every premium feature. They leave the lights on in rooms they aren't using, and suddenly your monthly operational expense, your OpEx, is ballooning completely out of control.
Yeah, that tracks perfectly. The rent doesn't just go up, it scales exponentially based on every single micro-interaction you have with the apartment.
Right.
You are charged every time you open the fridge, every time you turn a faucet. In cloud terms, you are hit with egress fees every time you move your own data, API call costs, and massive premiums for high-performance compute instances.
So eventually, the CFO looks at the monthly cloud bill and says, this is unsustainable. We are paying enough in rent every month to buy the entire building. We need to buy our own house.
That is the business deciding to repatriate workloads back on premises.
They realize that making a massive capital expenditure, CapEx, to buy their own servers will actually save them millions in the long run compared to bleeding operational expenses indefinitely.
The financial modeling often heavily favors on-prem for predictable, high-volume workloads. But to complete your analogy, here's the massive friction point these companies hit when they buy that house.
Okay, what is it?
They move their workloads back on-prem, they buy the servers, the storage, and the switches, but they quickly realize they left the landlord's beautiful, unified management portal back at the apartment.
Oh, wow. Yeah.
Now they own a house, but they don't have a universal remote. They are standing in the living room with 50 different apps on their phone just to run the house.
One proprietary app to lock the front door, a different app from a different vendor to adjust the thermostat, and a completely separate, non-integrating tool just to turn on the lights.
And that lack of a universal remote takes us straight into the core philosophy of what Supermicro is attempting to dismantle here.
Because the traditional hardware vendors didn't accidentally give you 50 different remotes. That was a deliberate business strategy, wasn't it?
Highly deliberate.
The source material specifically calls out competitors by name: HP, Dell, Lenovo, Cisco. It accuses them of trapping customers in traditional IT paradigms through proprietary tools.
It is the classic walled garden strategy, and it leads directly to vendor lock-in.
Right.
If you buy a rack of servers from one of these legacy providers, they will happily provide you with a very slick management dashboard. But that dashboard is meticulously engineered to only speak the proprietary language of their specific hardware.
So if you train your entire DevOps team for 2 years on how to use Dell's OpenManage or HP's ILO systems, your team becomes highly efficient within that specific garden.
But what happens 3 years down the line when it's time to upgrade your storage arrays, and a competitor offers a significantly better, faster piece of hardware for half the price?
You can't use it. Well, you can, but if you buy the competitor's hardware, it will not integrate into the management dashboard your team relies on.
Exactly. It becomes a rogue element in your data center. The friction of retraining your staff and running parallel disconnected management tools is so high that businesses simply surrender.
They overpay for inferior hardware just to keep it within the proprietary ecosystem they are already locked into.
You are held hostage by the management software.
You are forced to buy the proprietary coffee pods because the machine won't accept anything else, even if a better coffee is available.
Great way to put it.
Supermicro's presentation centers its entire value proposition on rejecting this model entirely, advocating instead for an open standard-based approach.
And the foundational technology making this possible is something called Redfish.
Right. Redfish is absolutely central to understanding the modern data center.
To understand why SuperCloud Composer is so disruptive, we have to look at what Redfish actually is. It is an open industry standard specification.
Meaning anyone can use it?
Exactly. It was designed collaboratively by the industry to deliver simple, secure, and universal management for converged hybrid IT and software-defined data centers.
It is essentially a universal API, a standardized language that any piece of hardware can use to report its health and receive commands.
And to understand where this universal language is being spoken, we have to look at the physical architecture of a server.
Redfish doesn't live in the main operating system like Windows or Linux.
No, it doesn't.
Yeah.
It is implemented in a specific hardware component called the Baseboard Management Controller, or the BMC.
Let's break down the BMC.
Think of the BMC as a tiny, highly resilient, independent computer physically soldered onto the motherboard of the main server.
Like a parasite.
More like a symbiote. It has its own processor, its own memory, and most importantly, its own dedicated network connection that is entirely separate from the main data traffic of the server.
Oh, I see. It's a completely out-of-band system.
Exactly. The BMC's entire reason for existence is to be the ultimate, unquestionable slice of truth for the physical health of that specific machine.
So if the main server's operating system completely crashes, like it gets a blue screen of death or a kernel panic,
Right.
the BMC is completely unaffected.
Unbothered. It is still awake, still monitoring the voltage of the CPU, the RPM of the cooling fans, the physical temperature of the chassis.
So instead of a human pushing a crash cart down an aisle to plug a monitor into a frozen server,
The administrator sits at their desk in another country, connects to the BMC over the network, and the BMC allows them to see the screen output, troubleshoot the crash, or physically cycle the power to reboot the machine.
the BMC is the digital crash cart.
It really is. And Redfish is the modern open standard language that allows external management software to talk to that BMC efficiently.
But here is the critical point of friction that Culp highlights in his presentation. If Redfish is a universally agreed upon open standard designed to make life easier for administrators, you would expect every major hardware vendor to fully embrace it.
You would think so, but no.
I was looking at this and it hit me as incredibly strategic, almost cynical. Culp explicitly states that competitors like Dell, HP, Lenovo, and Cisco have implemented Redfish, but they have intentionally limited their implementations.
Right.
Why would a company participate in creating an open standard, put it in their hardware, and then artificially restrict what it can do? It has to be a mechanism to enforce that walled garden, right?
It is a calculated protection of their proprietary ecosystems. Because if they implemented Redfish fully and transparently, any third-party management software could effortlessly monitor and control their servers.
They would be commoditizing their own hardware.
Exactly. By providing a limited Redfish implementation, perhaps only allowing it to report basic temperature, but not allowing it to update firmware or configure complex storage arrays, they force the customer's hand.
They force the customer to say, well, the open standard tool doesn't give me enough control. I guess I have to buy the expensive proprietary management software license from the vendor.
They are building an open door, but putting a proprietary lock on it, and only giving you the key if you stay entirely within their ecosystem.
That's frustrating. So Supermicro's counter strategy with SuperCloud Composer is to completely embrace the open standard.
Right. They are relying on Redfish intelligent agents to harvest metadata not just from their own hardware, but from any third-party device that speaks the standard.
This is the ecosystem-friendly promise of SEC. They're offering to act as the true universal remote.
Exactly. If you have a multi-vendor environment, say a legacy Dell server, a new Supermicro AI node, and a third-party network switch, SCC is designed to pull the Redfish endpoints of all those devices and pull them into a single, unified dashboard,
Breaking the vendor lock-in completely.
breaking it completely. And Culp breaks down the evolution of how we actually use these tools into 3 distinct tiers of management. It is a really helpful way to visualize how the scale of the problem expands.
Let's go through those. The first approach is the most archaic digital method, basic server management.
This is a strict one-to-one relationship. You open a web browser on your laptop, you type in the specific IP address of one server's BMC, and you log into its web UI. You are managing a single machine.
It's a huge step up from the physical crash cart. Sure, you aren't freezing in the data center,
Yeah.
but structurally, it is completely unscalable.
Very much so.
If you are managing an environment with 500 servers, you cannot realistically have 500 browser tabs open, logging into each machine individually to check if a hard drive failed.
No, it relies entirely on human polling, which means failures are often missed until they cause a cascading outage.
Okay, so what's tier 2?
The second approach attempts to solve this with a unified dashboard. This creates a one-to-many relationship. You use a tool to aggregate the status of many compute servers into a single interface.
So you have one pane of glass, and you can see the health of 500 servers at a glance. Much better.
Significantly better for visibility. But traditionally, these dashboards were still highly siloed by function. You could see all your compute servers, but you still needed a different dashboard for your network switches and a different one for your storage arrays.
You're still app switching.
Exactly. Which brings us to the third approach, the holy grail that SEC is targeting. True enterprise management. This is a many-to-many relationship.
In this tier, the management software transcends the silos.
You are utilizing a single unified platform to comprehensively manage compute hosts, storage clusters, and the network switching fabric all at once. It provides enterprise-wide visibility and control regardless of the scale.
And this transition to enterprise management relies heavily on a concept that sounds suspiciously like marketing jargon, but actually represents a massive structural shift in how data centers are built.
The software-defined data center.
Yes. What does it actually mean to define a physical building full of heavy metal racks with software?
It represents the death of cumbersome, rigid hardware provisioning.
Okay.
In the old IT paradigm, hardware was monolithic and inflexible. If a department needed a database server, you physically purchased a server with a specific ratio of CPU, memory, and local hard drives. It was a fixed asset.
Right.
If that database grew rapidly and needed more storage, but the CPU was barely being used, you were stuck. You had stranded compute resources that you couldn't easily reallocate, and you still had to go buy another physical storage array.
It was like buying a car where the seats, the engine, and the trunk were permanently welded together. You couldn't swap a bigger trunk in if you needed to haul more cargo.
Precisely.
Right.
A software-defined data center powered by architectures like SEC's Unified Fabric Director completely abstracts the hardware from the workloads.
So it stops treating a server as a fixed box.
And instead treats the entire data center as what Culp calls a collection of fluid resource pools.
Fluid resource pools. Okay,
Yeah.
so the physical hardware is still sitting in the racks, the CPUs, the NVMe drives, the GPUs, but the software layer sits above it all.
Right. It looks at every single component across the entire network and allows the administrator to dynamically slice and dice those resources on demand.
Through a scalable fabric.
Yes, you can instantly assemble a logical server tailored perfectly to a specific workload.
So an AI training model suddenly needs massive GPU acceleration and high-speed network throughput for, let's say, 4 hours. The software-defined infrastructure dynamically allocates those specific resources from the fluid pool. Right.
Exactly. It presents them to the workload as a unified system and then returns those resources to the pool when the task is done. The management software becomes the orchestrator of a highly flexible hardware symphony.
Okay, I'm completely tracking with the philosophy.
Yeah.
The open standards, breaking vendor lock-in, the beauty of fluid resource pools, it all sounds incredible on paper.
Yes,
But, so, as anyone who has ever worked in enterprise IT knows, the gap between a glossy presentation and a Monday morning deployment is usually vast.
Very.
Usually when a vendor promises to unify your entire global infrastructure, the unwritten reality is that you're going to have a team of expensive implementation consultants living in your conference room for 6 months.
Writing custom scripts just to make the dashboard work.
Yes. But Culp's presentation outlines a deployment process for SEC that is shockingly streamlined. He boils it down to day zero deployment in just 3 steps.
The material focuses heavily on minimizing the time to value. The 3 fundamental steps to stand up the architecture are: Step 1, deploy the SEC appliance. Step 2, deploy a managed supermicro switch for network reachability. Step 3, discover the devices.
Let's analyze the mechanics of each of those, starting with step 1. The SEC appliance itself, the actual software running this massive orchestration layer. Where does it live, and how restrictive are the installation requirements?
The flexibility of the appliance deployment is a major architectural advantage. It does not dictate your underlying infrastructure. You can deploy it in 2 primary fashions. First, as a bare metal host, meaning you dedicate a specific physical server to run nothing but the SEC operating system.
Oh, okay.
Second, you can deploy it as a virtual machine guest instance.
So if your data center is already heavily virtualized on VMware or a KVM hypervisor, you can just spin up a new VM and drop the SEC appliance right into your existing management cluster.
Exactly. And importantly, it supports different flavors of Linux kernels, ensuring it meshes with the security and operational standards your DevOps team is already comfortable with.
That makes sense.
But perhaps the most critical detail Culp mentions regarding deployment is that SEC supports both online and air-gapped installations.
An air-gapped installation. We touched on governance earlier, but let's dive into what an air-gapped system actually implies for an administrator.
An air-gapped environment means the entire local network is physically and logically severed from the public internet. There is no outside connection. Period. For highly secure environments, Defense Department networks, critical power grid infrastructure, core banking systems, and air-gapped architecture is an absolute non-negotiable mandate.
And many modern management platforms are essentially SaaS products, right?
Yeah.
They require a constant tether to the vendor's cloud to authenticate licenses or download updates.
Right. If you put them in an air-gapped room, they fail. The fact that SCC can be installed from offline media and operate completely autonomously without ever phoning home to the public internet makes it viable for the most secure enterprise environments on the planet.
So you have the appliance deployed, either on bare metal or a VM, online or air-gapped. Step 2 is deploying a managed supermicro switch. Why is the switch the crucial second piece of the puzzle?
The managed switch is the critical bridge for network reachability. Remember, SEC needs to constantly poll the BMCs of every single device in the data center using Redfish.
Right.
If the network topology is unstable, or if the routing between the management software and the out-of-band management network is complex and fragmented, the entire system collapses.
Because it can't see the endpoints.
Exactly. By deploying a specific managed switch as the core of the SEC network, you guarantee a robust, highly visible communication pathway. It becomes the central nervous system that allows the brain, the SEC appliance, to reliably send signals to the extremities.
Which perfectly sets up step 3, discovery. This is where the sheer mathematical scale of what we are talking about starts to become difficult to comprehend.
Scale is the key word.
The presentation highlights a feature called Pod View, which utilizes a Home AVIX feature to automatically discover hardware. Through this Pod View, the system supports the scaling and monitoring of up to 20,000 compute hosts.
20,000 individual physical servers. The density and complexity of an environment that large is staggering.
I can't even picture that many servers.
Decontextualize that. Culp is talking about the ability to build and logically organize a scalable superpod, a megapod, or a massive AI factory in minutes.
Building an AI factory in minutes sounds hyperbolic, like something out of a sci-fi novel. How is the software actually making sense of 20,000 endpoints without a human manually typing in 20,000 IP addresses and mapping them to physical racks on a spreadsheet?
It relies on deep automation and intelligent agents. As the devices are powered on and connected to that managed switch network we discussed in Step 2, SCC uses open protocols to broadcast and discover them.
Okay.
The system can automatically associate discoverable devices and map them to specific rack installations. The Pod View feature provides a deep visual representation of rack management.
So the dashboard isn't just a massive, unreadable list of IP addresses. It visually builds a hierarchical map of your data center.
Right, you can see a pod, click into it to see a row of racks, click into a rack and see the exact physical position of a specific server.
Yes, and that brings us to the operational reality of Day 2 lifecycle management. Once those 20,000 devices are discovered and mapped, what are you actually doing with them?
The depth of the telemetry SCC pulls goes far beyond a simple binary check of, is the server turned on or off?
Culp details a massive list of capabilities powered by intelligent agents utilizing a northbound API. And they even offer a software developer kit, an SDK, for deep integration.
Right.
Let's explore what kind of metadata these Redfish endpoints are actually feeding back to the administrator.
The platform provides comprehensive asset tracking at a granular component level. With just a few clicks, an administrator can identify a server by its IP address and logical node name.
Okay.
But they can also instantly pull its physical rack location, categorize it by product family, and drill down into the microarchitecture. It collects detailed CPU and memory configuration information. It tracks the exact firmware versions of the BIOS and the BMC.
And I noticed a specific bullet point about automated inventory management and serial number collection. I want to highlight this because unless you have worked in IT, you cannot fathom the amount of human misery involved in an annual hardware audit.
Oh man, the manual inventory audit is universally dreaded.
I have friends in the industry who recount horror stories of spending entire weekends with a clipboard and a flashlight, physically walking down the freezing aisles, contorting themselves behind racks, trying to read tiny smudged barcode stickers on the back of servers.
Yep.
Just verify for the accounting department that the hardware they bought 3 years ago is actually in the building.
It is an incredibly error-prone, time-consuming process that completely wastes the talent of highly paid engineers.
Absolutely.
SCC automates that entirely. Because the serial numbers are hard-coded into the hardware and accessible via Redfish, SCC continuously harvests that metadata.
So an administrator can generate a complete, accurate inventory report of 20,000 servers in seconds.
Entirely eliminating the flashlight and the clipboard.
Thank goodness. Beyond inventory, SEC handles full power management. It provides direct, secure links to the individual BMC web UIs if you need deep access.
It automates BMC firmware updates across massive clusters simultaneously, and it centrally collects hardware-level information.
But the feature that caught my attention as truly proactive is called Call Home.
Call Home fundamentally changes the maintenance paradigm from reactive to proactive.
How so?
Well, in a traditional setup, you often don't know a server component has failed until a user calls the help desk to complain that their application is throwing errors. You are relying on the symptom to diagnose the disease.
Which means the business is already losing money due to downtime.
Exactly. Call Home allows administrators to create highly specific policies and track key trigger alerts for every managed server.
Because SEC is constantly polling the hardware health via Redfish.
Right. It can detect anomalies before they cause a critical failure. If a memory module starts experiencing a high rate of correctable errors, or if a cooling fan drops an RPM, the hardware instantly calls home to the SEC appliance based on the defined policy.
So the system alerts the administrator that the hardware is sick before anyone in the company even notices a performance drop.
Yes. A technician can swap out a failing RAM stick during a scheduled maintenance window rather than scrambling during a catastrophic database crash on a Tuesday afternoon.
That alone justifies the management layer, in my opinion. But Culp's presentation pushes into even faster operational capabilities. Let's talk about the fast deploy mechanism for operating systems. The claim here is that you can deploy an OS to a bare metal server in seconds.
To understand how a multi-gigabyte operating system can be deployed and operational in seconds, we have to look at how SCC utilizes its artifacts repository in conjunction with a PXE service.
Okay, PXE service. This is a crucial concept. Let's
Okay.
break down the mechanics of PXE for the listener because it completely redefines how a server wakes up.
Right. PXE stands for Pre-Boot Execution Environment.
Pre-boot. Got it.
Think about how a normal computer works. You press the power button, the motherboard wakes up, and the first thing it does is look at its local hard drive to find Windows or Linux to load into memory.
Right. It looks internally.
But in a massive software-defined data center, managing local hard drives on 20,000 servers is highly inefficient.
And if the hard drive dies, the server is dead until a human replaces it and spends an hour reinstalling the OS from a USB drive.
Precisely. A PXE environment changes the boot order. When a bare metal server powers on, it doesn't look at a local hard drive.
It looks out to the network.
Exactly. The motherboard's network interface card initializes, reaches out across the network, and essentially broadcasts a message. I am a server with this specific MA address. I have no operating system. What am I supposed to be doing?
And in this architecture, the SEC appliance intercepts that broadcast.
SCC acts as the centralized PXE server. It maintains a secure repository of pre-configured, highly optimized operating system images artifacts.
So when it hears the broadcast from the bare metal server,
SCC instantly pushes the correct OS image down to the server over the network, directly into the server's memory.
the operational speed this unlocks is just incredible. Imagine a scenario where you are running an e-commerce platform and it is Black Friday. Traffic spikes massively, and your monitoring tools tell you that your web front-end servers are at 99% capacity.
You're about to crash.
You are about to crash and lose millions in sales. In a manual environment, you are doomed. But with SCC and PXE, you can physically power on 50 blank reserve servers. SCC intercepts their boot broadcast, pushes the web server OS image to all 50 simultaneously, and within minutes, they are online and handling the traffic spike.
Ensuring you meet your service level agreements, it is the ultimate manifestation of the fluid resource pool. Compute resources can be infinitely repurposed on the fly.
And this level of deep intelligence isn't just limited to the compute nodes. It extends deeply into the network fabric itself. SEC features a built-in network agent that provides support not just for Supermicro switches, but for switches running the open-source Sonic operating system, as well as proprietary third-party switches.
Right.
The capabilities of this network agent immediately brought a very specific analogy to mind. The presentation notes that this agent can identify switch ports that are colored, which allows it to determine the exact kind of physical device connected to that port.
Yes.
It can read the VLAN, the virtual local area network, presented to a switch port at a glance, and automatically determine the entire network topology in seconds.
It provides profound visibility into the MSC address tables, the top-of-rack switch provisioning, and the live running configurations, all without requiring the administrator to use a command line interface.
So imagine a massive skyscraper that has just been built. It's incredibly complex, thousands of rooms. But the architects lost the blueprints for the electrical system.
Okay.
If a normal person walks into the basement electrical room, they just see a terrifying maze of gray wires. They have no idea what connects to what. But the SCC network agent is like a master electrician with perfect vision. They walk into the room, look at the main breaker panel, and because they can read the subtle colors and frequencies on the wires, they can instantly draw you a flawless three-dimensional blueprint of exactly which wire goes to the coffee maker on the 40th floor, which one powers the elevators, and which one runs the HVAC system.
It removes all the dangerous guesswork from understanding how the entire enterprise is physically connected. That is a highly accurate visualization. Network topology maps are notoriously difficult to keep updated manually.
Because someone plugs something new in and forgets to write it down.
Exactly. SCC automates the blueprinting. But the management doesn't stop at compute and networking. Some of the most cutting-edge features Culp details revolve around environmental controls. SCC includes a universal agent specifically for PDU management.
PDUs being power distribution units. To oversimplify, these are the massive, highly intelligent power strips that run down the back of the server racks, providing electricity to the hardware.
They are far more than power strips today. SCC interfaces with these smart PDUs to allow remote outlet operation.
So an administrator can physically power cycle a single outlet on a rack on the other side of the planet.
Yes. But more importantly, SCC collects rich, real-time power utilization data at both the bank and the individual outlet level.
Why is that level of granular power data so critical?
It allows the enterprise to continuously monitor its power usage effectiveness, or PUE. Power is one of the highest ongoing operational costs of a data center.
So if you can see exactly which workloads are consuming the most wattage, you can optimize them.
Furthermore, the PDUs act as environmental sentinels. They pull in vital sensor data like humidity and temperature right from the racks.
Which is an absolute life or death metric for hardware. If the HVAC system in an aisle fails, you need an alert that the temperature is spiking in rack 14 before the servers literally melt themselves into slag.
Exactly. And speaking of keeping things from melting, this brings us to the truly next-generation capability Culp highlights: liquid-cooled data center management.
This is fascinating to me.
This is where the physical reality of modern workloads forces an architectural evolution. As we push deeper into AI training and high-performance computing HPC, we are utilizing massive, ultra-dense clusters of GPUs.
Right.
The thermal output of a modern NVIDIA or AMD GPU is staggering. Traditional air cooling, just blowing cold air across a heatsink with a fan, has hit the limits of physics. It simply cannot dissipate the heat fast enough.
The servers generate more heat than the air can carry away.
Precisely. The industry is rapidly adopting direct-to-chip liquid cooling. You are literally pumping specially formulated coolants directly over the processors.
Wow.
And managing the infrastructure that pumps that the cooling distribution unit, or CDU, is critical. If the CDU fails, the AI cluster will overheat and trigger a thermal shutdown in seconds.
And SCC is managing this liquid cooling system in real time. It's constantly pulling critical sensor data from the CDU. What's incredible is how all of this converges.
It all comes together.
SCC takes the compute health data from the BMCs, the network topology from the switch agent, the power consumption from the PDUs, and the thermal metrics from the liquid cooling CDUs, and feeds it all into an easy-to-use, customized, data-driven dashboard.
It provides holistic, real-time accelerator utilization metrics for the most advanced AI workloads on the planet. It is the ultimate realization of the many-to-many enterprise management philosophy.
Every silo is broken down.
All telemetry, from the voltage of a single RAM stick to the flow rate of the liquid coolant, is unified under one single pane of glass.
Okay, here is where I have to pause the celebration and ask the deeply cynical business question.
Hit me.
We are talking about a software platform capable of managing 20,000 liquid-cooled AI hosts, deploying operating systems over the network in seconds, proactively predicting hardware failures, and pulling real-time metadata from multi-vendor network switches.
It's a lot.
In the modern software industry, a tool this powerful usually comes with an incredibly complex, aggressively expensive, recurring monthly subscription model that bleeds IT budgets dry. How on earth do you actually pay for SuperCloud Composer?
This is perhaps the most disruptive and strategically fascinating part of Supermicro's entire presentation. The economics of scale they're proposing completely buck the prevailing industry trends.
Okay.
There are no subscriptions.
Wait, zero recurring subscription fees?
None. Every software license for SuperCloud Composer is perpetual in nature.
Okay, we need to carefully unpack this licensing model because it is granular, it relies on specific hardware identifiers, and the mathematics of it dictate the entire financial strategy for deploying the software. There are two main tiers or two distinct types of licenses you can purchase.
Correct. The foundational tier is known as the DCMS single license. DCMS stands for Data Center Management System.
DCMS. Got it.
This is the absolute baseline perpetual license required to turn on the Redfish management functionality for a server's BMC.
So no matter what your grand ambitions are, you cannot do anything in SEC without first owning a DCMS license for the target machine.
Right. It is the fundamental prerequisite because, as we established earlier, SCC utilizes the server's BMC as its ultimate source of truth.
And if the Redfish endpoints on the BMC are not unlocked by the DCMS license, SEC is blind to that piece of hardware.
Exactly. And there is a deeply specific, crucial detail here about how this software license is fundamentally tied to the physical hardware. It is permanently wedded to the MMASH address of the BMC, isn't it?
Yes, let's clarify that mechanism. A MS address, Media Access Control address, is a unique, permanent identifier assigned to a network interface controller at the factory.
Right. It is physically hard-coded into the hardware.
When you purchase a DCMS perpetual license, that specific license key is generated against and permanently tied to the unique MS address of that exact server's BMC.
I want to look at this from a CFO's perspective because it completely shifts how you account for software.
Yeah.
If I buy a server today, let's say an X13 generation machine, and I purchase a DCMS license for it, I own that software capability forever, or at least for the life of that physical box.
Right.
But Culp makes a very specific point to clarify what happens during a hardware refresh cycle. What happens if, 3 years from now, I decide to upgrade my data center and replace that X13 server with the next generation, an X14?
This is where the hardware-locked model enforces its boundaries. If you do a physical hardware upgrade from an X13 to an X14, you are installing a completely brand new motherboard.
Right.
That new motherboard contains a brand new BMC chip, which inherently possesses a completely new, unique MSC address.
Ah.
Because the MSC address has changed, the original perpetual license you bought 3 years ago no longer applies to the new hardware. You cannot float the license to the new machine.
So you have to buy it again.
You would need to generate and purchase a new DCMS single license key to unlock the Redfish functionality for the new X14 generation server.
That makes perfect strategic sense from a capital expenditure model. The software license isn't a floating subscription. It is amortized over the specific physical life cycle of the hardware it manages.
Right. When the hardware retires, the license retires with it. You treat the management software as a fixed cost of acquiring the server itself.
Yeah.
Okay, so that is the baseline DCMS license. What is the second tier?
The second tier is the SDDDC single license, software-defined data center. This is the premium license required to unlock the full many-to-many enterprise management features within SEC.
So if I have a smaller business and I only purchase the baseline DCMS licenses, I can still use SEC, but I am limited to basic one-to-many server management.
Right, you can see server health and update firmware.
But if my ambition scales, if I want to manage my complex network switches, monitor the PUE on my smart PDUs, track the thermal data from my liquid-cooled CDUs, and utilize advanced real-time telemetry, that is when I am required to purchase the SDDDC license.
Exactly. It is a highly modular approach. You are not forced to buy massive, complex enterprise features if you don't need them.
But your infrastructure scales to the point where you want to consume those advanced features in a production deployment. You purchase both the DCMS and the SDDDC licenses for your nodes.
And again, both tiers are perpetual. You buy them once, no monthly operational fees.
But introducing a massive software platform to a global enterprise is a huge risk. What if I am an IT director and I love the philosophy, but I am not ready to commit hundreds of thousands of dollars to the full enterprise suite without proving that it actually works in my specific environment?
Supermicro mitigates that risk by offering a highly generous 90-day free trial for the advanced SDDDC tier. And the mechanics of how they issue this trial license are quite clever, ensuring it is secure but easy to deploy.
Let's get into the weeds on how you actually acquire the trial. It involves a different MAC address than the servers you are monitoring, right?
Correct. The trial license is generated based on the MEC address of the management node itself, the specific machine or appliance where the core SCC software is installed.
Okay, so if you installed SCC on a dedicated bare metal host, the trial key is generated against the physical LAN and MAC address of that host.
If you chose to deploy SEC as a virtual machine, the key is generated against the virtual NIC0 MAC address assigned to that VM by the hypervisor.
You capture that specific management MAS address, send it to the Supermicro PM team, and they turn around and hand you a trial key.
Right, and that trial key is incredibly powerful for a proof of concept. It lasts for a full 90 days, and it instantly unlocks up to 200 monitored systems with full, unrestricted enterprise management functionality.
200 systems for 90 days. That is more than enough time and scale to prove the value to a skeptical CFO. But to truly understand how this perpetual MSC-based licensing model actually plays out in the real world, how the actual budgeting and math work on the data center floor, we need to look at specific examples.
The reference designs are the best way to visualize them.
Yes, the source material provides 5 very specific real-world data center rack reference designs, and Culp actually walks through the license map for each one.
This is crucial because it perfectly illustrates how flexible and sometimes surprising this licensing philosophy is when applied to different architectures.
Let's go deep into these, starting with Design 1.
Design 1 represents a standard U.S. data center rack setup. It is a very common baseline architecture.
Okay, picture the physical rack. At the very top, providing the network backbone, we have a management switch. Culp specifically notes it's a typical 35NT48 Supermicro switch.
Below that switch, we have the management node, a big twin server, and that specific node is where the SEC appliance software is actively running.
And then, filling out the rest of the rack, we are monitoring 12 compute host nodes.
To clarify the density, he breaks down the physical chassis containing those 12 nodes. It's built using 2U 4-node configurations. They have 3 of these specific chassis in the rack.
Okay, so 4 compute nodes per chassis multiplied by 3 chassis gives you the 12 individual server nodes that actually run the company's workloads.
So, I am the IT director. I have 12 compute nodes generating value for my business that I need to manage. What exactly do I have to purchase for a fully licensed official production deployment of SEC?
You need to establish the baseline Redfish communication for every single workload server. So you must purchase 12 perpetual DCMS licenses.
Furthermore, you want to monitor all of them using the advanced enterprise features, so you also purchase 12 perpetual SDDDC licenses.
Okay, the math there is simple, 12 and 12. But wait, what about the management infrastructure itself? What about the 3748 network switch at the top of the rack? And what about the big twin server that is actually running the SEC appliance? Do I have to buy licenses to manage the management tools?
This is a crucial point of leverage for the customer. The answer is no.
Oh.
Supermicro's model does not penalize you for the infrastructure required to run the software. The management switch does not require an SDDDC license to be monitored and managed by the network agent. And inherently, the SEC appliance cannot logically monitor itself.
Therefore, you consume 0 licenses for the management switch and the SEC appliance hardware. You only pay for the specific payload-bearing compute hosts you are actively managing.
I love the economics of that. You are paying for the freight, you aren't paying a tax on the delivery truck.
Exactly. Okay, Design 2. This is where the physical architecture shifts to address the thermal challenges we discussed earlier. A liquid-cooled rack solution.
The physical layout here is slightly different to accommodate the cooling infrastructure. We again have the unlicensed management switch and the unlicensed management node running the SEC appliance.
For the payload compute, we have a 2U 2-node configuration, and they have 2 of these chassis. So 2 nodes times 2 chassis equals 4 standard compute nodes. Additionally, they have 1 heavy-duty GPU-monitored host for specialized tasks.
Let me calculate the licensing for the nodes. 4 standard compute nodes plus 1 GPU node equals 5 total payload nodes in the rack. So following the rule, I need to purchase 5 DCMS licenses to unlock Redfish and 5 SDDDC licenses for full enterprise monitoring.
That math is exactly right for the compute hardware. But here's the critical twist regarding the environmental hardware. What about the cooling distribution unit, the massive CDU that is physically pumping the liquid coolant through the entire rack to keep that GPU node from melting?
Right. If the CDU is feeding real-time thermal telemetry into SCC, does monitoring it consume a license?
Supermicro does not require a license today for the CDU itself. You gain the ability to comprehensively manage and monitor the mission-critical liquid cooling infrastructure entirely for free under this model.
That is a massive strategic advantage. You're getting advanced real-time telemetry on the most critical environmental safety system in the rack, and it doesn't cost an extra dime in licensing.
Okay, let's look at Design 3. This setup is all about maximizing high-density compute, the Superblade architecture.
A blade architecture is designed to pack a massive amount of compute power into a very small physical footprint by sharing power and cooling infrastructure. In this specific design, Culp outlines an 8U enclosure that contains 20 individual blade nodes, and they have deployed 2 of these dense enclosures in the rack.
So 2 massive enclosures multiplied by 20 blades each. That is 40 individual compute nodes stacked incredibly tight. Plus, of course, the unlicensed management switch and the appliance node at the top. The math seems straightforward. 40 payload nodes means 40 DCMS licenses and 40 SDDDC licenses.
The core math is correct, but managing a blade enclosure introduces a unique piece of hardware called the CMM, the Chassis Management Module.
What does that do?
In a blade setup, the 40 individual blades don't usually have their own dedicated external network ports for management. It would be a cabling nightmare. Instead, the management switch connects directly to the single CMM, which acts as the intelligent interconnect, routing the management traffic to the individual compute blades inside the enclosure.
So the CMM is doing a lot of heavy lifting for the management network. Does the CMM itself require a license?
It does not. Supermicro maintains its focus on the payload. Licenses are only consumed on the individual compute blades themselves. The chassis management module, despite its critical role in the enclosure's architecture, is entirely exempt from licensing fees.
That hardware agnosticism is incredibly consistent. They're ruthlessly focused on only taxing the actual endpoints doing the computational work. Speaking of heavy computational work, let's look at Design 4. We are stepping into the absolute heavy hitters of the modern data center, NVIDIA Grace Hopper AI systems.
This rack represents a dedicated AI factory setup. It is populated entirely by immensely powerful, incredibly expensive NVIDIA Grace Hopper nodes. The design details 5 1U servers, what they classify as CG1 nodes. And they also have 3 larger 2U 1-node systems, the CG2 nodes.
So 5 of the 1U nodes plus 3 of the 2U nodes equals 8 total NVIDIA Grace Hopper systems in the rack. Now these nodes cost an absolute fortune compared to a standard web server. Does the licensing cost scale up based on the immense computational power or the high financial value of the hardware being managed?
No, it does not. The management framework is completely blind to the underlying cost or computational capability of the node. The math remains identical to the cheapest web server. You have 8 systems, so you purchase 8 DCMS licenses and 8 SDDDC licenses.
The simplicity democratizes the management layer, making it highly predictable for budget forecasting, even when deploying bleeding-edge AI hardware.
Which brings us to the final configuration, Design 5. This features AMD H100 GPU servers.
This is the most streamlined rack example. You have the unlicensed management switch, the unlicensed 1U appliance node running SEC, and exactly 2 AMD-based GPU payload servers.
Following the universal rule, 2 payload nodes means 2 DCMS licenses and 2 SDDDC licenses. The baseline math is incredibly straightforward once you internalize the payload rule.
But we have to revisit the 90-day trial rule. Culp explicitly laid out what happens to the math if you deploy these exact same 5 reference designs, but you decide to activate the free trial before committing to the enterprise purchase. The financial equation changes dramatically.
The trial rule is highly specific in its application, but it applies universally across every architecture we just discussed, whether it's a dense superblade enclosure or a rack of expensive NVIDIA AI nodes.
Let's trace the logic. If an administrator activates the 90-day trial using the AMNSE address of their management node, that trial instantly grants them 200 SDDDC enterprise licenses for free.
So in all 5 of those reference designs, the cost for the advanced SDDDC tier drops to exactly 0 during the trial period.
However, this is where many administrators misunderstand the structure. The free trial only covers the advanced enterprise tier. It does not cover the foundational Redfish tier.
So even if you are running the free trial, you cannot escape the baseline requirement. You still absolutely must purchase the perpetual DCMS licenses for whatever specific nodes you intend to monitor.
Exactly. The DCMS license is the physical key that unlocks the door to the BMC. You must buy the DCMS licenses to turn on the Redfish functionality so that the hardware can even speak to the network.
Once that foundational DCMS key is purchased and active, the free trial key acts as a multiplier, turning on the advanced enterprise analytics, the liquid cooling management, and the massive dashboard capabilities on top of it.
And it is crucial to remember that after 90 days, that SDDDC trial simply deactivates.
And this highlights the beauty of the perpetual model. Let's say you run the trial on the AMD GPU setup in Design 5. You bought the 2 DCMS licenses, and you use the free trial for the enterprise features. On day 91, the CFO decides that they don't want to spend the money on the enterprise tier.
You don't lose access to your system entirely. Because you purchase those DCMS licenses, you own them forever. You can still use SEC for basic server management, power cycling, and firmware updates.
The system just gracefully downgrades, removing the advanced telemetry and environmental dashboards. It doesn't break, it just scales back to the baseline you paid for.
It is an exceptionally low-risk mechanism for an enterprise to test the viability of a software-defined data center without risking total operational paralysis if they choose not to upgrade.
Okay, we have covered an immense amount of highly complex ground today.
We started by mapping out the massive philosophical and economic shifts driving workloads away from the ballooning OpEx of the public cloud, repatriating them back to on-prem data centers for the sake of predictable CapEx and rigid governance.
We explored the inherent dangers of vendor lock-in, exposing the walled garden strategies of legacy vendors, and analyzed how embracing open standards like Redfish and fully utilizing the out-of-band capabilities of the BMC provides a pathway out of that proprietary trap.
We looked deep under the hood of SEC, discovering how a single, flexible appliance can use a network agent to map complex topologies like a master electrician, how it can utilize PXE to deploy operating systems to bare metal in seconds to meet traffic spikes, and how it can scale effortlessly to monitor 20,000 liquid-cooled nodes.
And finally, we walked through the exact, unyielding math of how to license everything from a basic storage rack to a cutting-edge NVIDIA AI factory, entirely avoiding the nightmare of recurring subscription fees.
It truly highlights the incredible journey this industry has taken. We have moved from the slow, physical constraints of the freezing data center and the squeaky crash cart to a reality of truly fluid, instantly scalable, software-defined infrastructure.
But before we wrap up this deep dive, there is one final, somewhat provocative thought I want to leave you with, building directly on the capabilities of the open APIs we've discussed today.
Ooh, I love a good provocation to end on. Where does this technology logically lead us next?
We've spent this time analyzing how SCC feeds real-time telemetry power consumption from the PDUs, thermal data from the liquid cooling CDUs, deep hardware health metrics into a single comprehensive dashboard via its northbound APIs and SDKs.
Right.
Right now, this system is designed to empower human administrators. It allows a DevOps team to build, monitor, and manually scale massive AI factories in minutes. But as these AI workloads continue to grow exponentially in complexity, requiring dynamic surges in power, aggressive spikes in liquid cooling, and instantaneous resource allocation.
Yeah. Where is the friction point?
The friction point is human reaction time. How long will it be before the AI models themselves realize that waiting for a human administrator to allocate resources is too slow?
Oh, wow.
What happens when a massive AI training model, recognizing in real time that it needs a massive surge in compute power to finish a complex algorithmic calculation, simply bypasses the human entirely?
You mean it manages itself?
What if the AI model utilizes these exact same open APIs to interface with SEC directly? It could autonomously provision its own bare metal servers via PXE, adjust the power flow on the smart PDUs, and proactively increase the pump speed on the liquid cooling CDU for its own GPU cluster, all in milliseconds.
Well,
if the infrastructure is truly software-defined, entirely fluid, and governed by universally open standards, at what point does the AI become its own DevOps administrator, independently managing, scaling, and physically cooling its own hardware environment based entirely on its own real-time computational needs?
okay, that is a brilliantly wild thought to leave off on.
Yeah.
An AI sending an automated command through a Redfish endpoint to literally turn up the liquid cooling on its own physical brain because it knows it's about to think too hard.
Exactly.
If that is the future, the era of the crash cart is officially dead and buried. To everyone listening, thank you so much for joining us on this deep dive into the architecture and economics of the modern data center. Keep questioning the physical systems running the digital world around you and keep learning. We will catch you on the next one.